Welcome. We're going to discuss how to view a line integral of a vector field as a special case of the line integral of a scalar function. And I've got the result of how we evaluate a line integral of a scalar function here on the screen. Remember, the main idea is to pull the problem back via parameterization, and that parameterization is typically by the curve r of t, to computing a line integral over an interval on the number line, hence why we end up with a scalar single variable integral here on the right hand side. And one thing to note, as we've seen, is that line integral is independent of the parameterization. Okay, meaning it doesn't matter how you parameterize your curve C. So for instance, if we have a circle, for instance, it doesn't matter if we have a curve going counterclockwise or parameterized counterclockwise versus clockwise for the general line integral of a scalar function. However, we have seen that it does matter for line integrals for vector functions, and part of this is understanding this. This video is going to be understanding this notation here, f dot t ds. All right, so these two notations are equivalent to one another. We treat them as one and the same. The expression over on the right hand side here tells us how we evaluate that line integral. Notice it's f of r of t, so capital F here is the vector field, little r is the parameterization of the curve, and we take that vector and take the dot product of that with the first derivative, right, with the tangent vector r prime of t. And notice here that will depend on the parameterization. Just as a quick review, if we think about above here, the curve on the left hand side being the curve C, and the curve on the other side would, since we've changed the orientation, we could think about as the opposite, or negative C. Then if we were going to write out a line integral for a function over that circle, and then we wanted to compute the line integral of the vector field over the curve negative C for the same vector field, what we'd end up with is the opposite result. So if we change the direction of the orientation, then we're going to get the opposite result. All right, now we're going to try to spend a little time to see how we can view this line integral as a special case of the case above, where we have a line integral of a scalar function. Now, it's not going to, in that case, we're going to have to be careful about the parameterization, because when we talk about the line integral of a vector field, the curve is going to be given a specified orientation. All right, but we know from our previous work that if we have a vector valued function, and if its first derivative is not 0, then we know that the tangent vector r prime of the derivative vector r prime of t will be a tangent vector, and moreover it's going to point in the direction of increasing parameter. All right, so it goes along the curve, and therefore if we normalize it by taking its length and taking that vector and dividing it by its own length, as I have written here, we're going to have a unit vector, and it's going to be a unit vector along the curve, and therefore we can think about capital T, which represents the unit tangent vector, as the same as r prime over the length of r prime. Alright, so if we're given a smooth curve, again that's the assumption we're typically making here, smooth just means at every point along the curve, if you have your parameterization r of t, that for every t value the first derivative vector is not the 0 vector, it does not have length 0. That prevents abrupt changes to the graph. It prevents corners or cusps from happening in the graph of the function. So if we're given a smooth curve, then we can choose and we choose the parameterization r of t to match the given orientation of the curve C, then we know that the unit tangent vector will line up with the derivative divided by its length. Alright, so that will be the unit tangent vector we're referring to up in the line integral. Alright, now what we're going to do is we're going to take that expression and we're going to plug it in to the line integral of a scalar function, but we have to do that if we view the quantity we have toward the bottom here, f dot t, we have to view that as a scalar function. And what is that scalar function? It's going to be the vector field capital F taken with the dot product in the unit tangent vector. Alright, so we're thinking about that as a scalar function, but again, we've got to be a little bit careful here. Viewing it that way, we are taking into account the orientation of the curve. We can't just choose any parameterization of the curve. It has to match the orientation of the given curve. Alright, now if we do that, what we're going to do next is just substitute that in to the expression for the line integral. So what we're going to do is we're going to take capital F dot t, and we're going to substitute that in there for little f of r of t. Alright, so let's do that work now. Alright, so substituting that in there, we just need to rewrite this. So we're going to have the integral from a to b. Now we need to leave a little bit of space here. Little f we're going to replace with capital F of r of t dotted with capital T of r of t, or of t we should say. And that's going to be times the length of the first derivative vector of r of t of the parameterization. That's true for any scalar function. Our scalar function this time is little f. Alright, now what we're going to do is just replace what capital T is equal to inside that integral. Alright, so this is equal to the integral from a to b of, now we have capital F of r of t. As we said before, the unit tangent vector, as long as we're talking about a smooth curve, we can rewrite that a smooth curve that aligns with the parameterization can be just the normalized derivative vector. So we can substitute that for r prime, substitute in r prime over the length of r prime for capital T for the unit tangent vector. And then we notice something happens here, because we also have to then multiply that result of that dot product by the scalar, the length of the first derivative. Assuming that's non-zero, what we can do here is cancel out these magnitudes. We can bring that into the dot product and multiply one of those vectors by that magnitude, and we can multiply therefore the second vector by the magnitude and cancel that out. So what does that leave us with then? We are just left with the integral from a to b of f of r of t dotted with r prime of t. And again, that's what we have seen before in our work on line integrals of vector fields. Alright, so all we've done there is show, and I'm just going to write this backwards now, that we can view the line integral of the scalar function. We can view a line integral of a vector field as the line integral of a scalar function, provided we're assuming that little f is f dot capital T, meaning it's the vector field dotted with the unit tangent vector, if we choose the curve r of t appropriately. Again, that's an important assumption here. We are choosing r of t to match the orientation of the curve. Now if we do that, the work we just shown has allowed us to view some of these notations as the same, or view them in the same light. So that's some of the notation that we're going to see in our homework and in textbooks, is f dot dr, right, for the line integral of a vector field. We can also think about that as the line integral of a scalar function, where that scalar function is capital F dot t. Okay, and again, one thing I just want to point out here is, notice we have this dot dr notation over here, versus over on the right side we've got with integrating with respect to arc length ds. Okay, so again, we can view that, we can view always a line integral of a vector field as the line integral of a scalar function if we choose the parameterization correctly. So that's the assumption on there. We got to be careful to make sure we have that caveat. Alright, and that just helps us to understand this notation behind this line integral here. Alright, where we have f dot t ds. Again, the ds part means we're taking the line integral with respect to arc length. Alright, just a couple more things to note going forward here. Alright, and I'm just going to mention that in the subsequent videos we're going to talk about surface integrals of both scalar functions and vector fields, and we're going to see a similar kind of analysis happen, where we're going to view a surface integral of a vector field as a special case of the surface integral of a scalar function. Like we're doing here, we're viewing the line integral of a vector field as a special case of the line integral of a scalar function. Again, it's going to depend on the parameterization, as I keep repeating. Alright, just a quick view to think about how we visualize this. We've got a curve C, right, that's immersed into a vector field. Then what we're thinking about here is that along the curve we can think about two unit vectors. One of them is the tangent vector, capital T. The other one would be the unit normal vector to the curve, and we're not going to have any homework on this, but I'm just going to mention it briefly. What we're looking at with the line integral of f dot t with respect to arc length along that curve is the contribution that the vector field has in the tangential direction, and we call that integral the work integral and also the circulation integral, all right, if it's a closed curve. We could similarly, all right, and one thing we said in previous work with that integral, what it does is it measures the net effect of the vector field f in the tangential direction or along the curve. Again, it measures the net effect of the vector field along the curve, along the tangent to the curve. We could similarly define it for the net effect for the normal component of the vector field if we used the new scalar function, this time f dot n. All right, I'm not going to go into any more detail, but you can look at the textbook for that. All right, and that's called the flux integral. And that will be it for this video.